Hello and welcome to our webinar, Things to Keep in Mind While Scanning, Get Excellent Data to Work With. With me here in the call is Richard Steffen, the CTO of PointCap and the founder. My name is Martin Grana. I'm an R&D engineer for PointCap and I'm the head of the support team. And as the title already says, we are going to give you some tips and tricks on the theoretic basis to get very good scan data. Then let's dive right into our table of contents. We are today only going to speak about terrestrial scanning, and not about mobile mapping scanning. And our first point is project planning, what you should do before you go into the field, what you have to do in the office directly. The next point is the scanning, what you need to do in the field, what are some requirements to do in the field. And lastly, we are talking about the registration itself, the theory behind it, and some more ideas or the models behind it, the mathematics. So let's go into the project planning. The requirements you have with your with the customer, what the customer says to you, the time equals money, what you have to do there, or what are the time-saving things to know, and the planning itself. Requirements. What does the customer want and need? And what do you advise the customer to have? Normally, the customer comes to you and tells you, I want super high accuracy with all points possible, and of course color and great point density. And afterwards, he only wants to have a cut drawing. So you have to advise your customer to give him a good offer to the best things necessary. So we are talking about accuracy and point density, what is necessary. What is he going to do with the point cloud? Is he just processing it to a BIM model or to a cut drawing? Or does he want to use his point cloud for presentation? So is color required or not? Or can you just scan with intensity? Because this is a huge time savior, as we can see in the next slides. Another point is the accuracy. There is always the accuracy mentioned by the customer that he says he wants the best accuracy possible. The question is he meaning the global accuracy? Is he meaning the local accuracy? Or does he even know what accuracy means? And what are the influences on the accuracy? And another thing is the verification on your side. How do you verify that you scanned everything properly and that the registration was a success? These are things you need to make sure beforehand. Let's talk a little bit about the global versus local accuracy. For example, here we have two scans. On the left hand side, you see a wall which was scanned not with a lot of resolution. So there are a lot of holes in it. You see here all the single points. And you see the wall is more or less flat. And on the right side, you see the same wall now with two scans registered together. And you see there the walls are not directly over each other. They are around 1 millimeter, 2 millimeters apart from each other. And this is a registration error, which you get in addition. So on the left-hand side, you can say you have a local accuracy from the scanner, which is normally around 1 millimeter. And on the right-hand side, you have the accuracy with two different scans, a global accuracy of around 3 millimeters or something like that. Richard, do you have anything to add on these slides so far?
No, I just want to mention that everything we present here Should be scanner independent. Yeah, as it doesn't matter. It's a Faro scanner or a Trimble or a ZF or a Leica scanner. It's the same. Yeah, the same properties and the same problems we take on here.
If we, yeah, just to add to that, if we present something number specific, we have written down on which scanner we are elaborating our numbers here. But the general ideas are, of course, yeah, used in every scanner. Okay, then after the project planning and the requirements, let's talk about the time equals money. When you have discussed with your customer if you need color or not color, and you know the point density your customer wants from you, so you can decide on which resolution you're going to scan, what are the distances you're going to scan. Then you have to estimate how many scan positions you are going to need. Are there a lot of dead ends? Are there things where you need more scan positions to capture it more accurately, more densely? And what is the data accuracy which you want to achieve at the end? And what do you need for that? For example, do you need to bring it some geodetic points to get a better accuracy? Or is it just sufficient to slap together 5 scans and have a really quick floor plan? So let's talk about the scanning times first. We have here a Faro Focus S350 graphics. We have here the resolutions with the quality above here on the x-axis. And on the y-axis, we have the time in minutes, as you can see, 1 hour. The intensity is visualized in blue. And if you add color, we have topped it with the orange one on top. As you can see, the scanning times for full resolution and high quality are getting very big, and there are not many people who are needing to scan with full resolution or with a half resolution of the scanner. So we have the same graphic again, but we have stripped that down so you can see the differences in time scanning a lot better, because here we are only talking about minutes of a single scan. But what you can see here very clearly is if you need to capture every scan with color, this will add up a lot and you will need a lot more time to scan the complete project. If you just are able to scan it with intensity, it will be a lot faster. And this will, of course, save a lot of time and will cost you less time and therefore the customer less money. Next one is the import times. How long do you need to import your scans after scanning into your computer system which you are using? Of course, if you are using the software manufacturer's the scanner manufacturer's software, like for example, you have a Leica scanner and then you're going to register with Cyclone, or you have a Faro scanner and you're registering with Faroscene, these import times are not given. But if you take a third-party application like Scantra or PointCap, then of course you need to import the scans first. And it's around if you double the resolution, like going from 1/4 resolution to 1/2 resolution, then the time you need to import the scans will be ×4. And as you can see, if you have color here, intensity and color which you import, it will take a lot more time than only importing intensity. One more thing to think about in this graphics is not only the time consumed here, but this is only the import time of one single scan of Faro raw data. In this case, if you would have the perfect computer, so an unlimited amount of RAM and yeah, a very good CPU. But for example, if your RAM is not unlimited, as everybody's is, perhaps then you're only able to import one scan at one time, but you would be able to import 2 scans with a half resolution at the same time, meaning you can import them parallel, and then of course these import times would significantly change. So this is another thing. If you have lower resolution, you would be able to import a lot faster. So this is coming on top of the scanning time, of course, and the processing time which you will have. Speaking about point density, you see here again on the x-axis the resolution of the scanner, and on the y-axis the point spacing in 10-meter distance. So, for example, with this 1/32th resolution, you have around every 5 centimeter one single point. The more points and the higher the resolution, the more data you acquire and the more you have to store, of course. But it's just there so you know around what your point spacing might be and how many points you need at each position to visualize certain things. The beam divergence is here our next topic, meaning if you want to capture certain things, you have to make, or you have to know that your scanner is sending out some data, a beam, and the farther away your point is, the spot size is getting a lot bigger. So if you are scanning things which are very far away from you, then your point might not only hit a single area, but it's getting a lot bigger, and your feedback will be a wider area. And because of this, for example, corners of rooms are always getting round because this beam is hitting all walls around the corner and not the corner directly, and it's getting worse the more far away you are from this corner. We have here graphics of the beam divergence from a focus scanner. As you can see, the spot size is getting very huge the higher the distance to your target. It doesn't matter in the low range because here it's very small and the point resolution is normally not high enough to affect this, but with a higher distance to your area, this is getting an influence. Another thing you have to keep in mind is the accuracy itself of your single points. For example, in this graphics, we have our scanner here, and we are scanning a point, and the farther the point is away, the accuracy of the point reduces because of one thing, of course, the atmosphere, which is here at play because you're scanning a lot wider. Another thing is the mechanics of the scanner. In this overview here, we have the graphics of the accuracies in separated into the angle of the scanner and the distance itself. You see that the distance accuracy is very small in comparison to the accuracy of the angle, because on huge distances the angle has a much more impact due to the nature of angles. Richard, do you have to add something so far to these slides?
Can you go one slide back to 14? So you see the accuracy of a point. So this means here we visualize the error ellipses where the point measurement can lie in. And it depends on the angular accuracy. So this is the horizontal or vertical angular accuracy of the scanner. it comes from the mechanics and how well the scanner can measure the direction of the beam. And the second one is the distance. Martin mentioned already, it depends on also on the atmosphere. This is the parts per million usually. And of course, if I go farther away, then the angular accuracy will double if you double the distance. And in 300 meters, in the next slide, you see already we have angular accuracy by 200 meter of 2 centimeters. So means if you want to measure, let's say you are in the outdoor field and you want to measure the distance of 2 points in one scan at the distance of 200 meters, then this distance measurement cannot be more accurate than 20 millimeter. Yeah, this is you need to keep in mind when you provide measurements from terrestrial laser scanning. Okay.
Thank you. We have here a conclusion for the beam divergence and single point accuracy. The beam divergence, you have the reflected waveform has multiple peaks in time diagram, meaning there are multiple peaks which are coming back to the laser scanner and which could be interpreted as a point. And normally you just compute the mean from these different peaks, but then you might get ghost points on edges of tables, for example, or on other edges. And as Richard already mentioned, the single point accuracy is very important for A, the adjustment, and B, for distant measurements in your project. Because if you measure huge areas with only one scan and then your measurement is 2 centimeters off, you have to tell your customer that you have this accuracy and that you are not able to provide them something better. Coming to the next point, the planning itself. If you are going to plan how you are going into the field, the first thing is use a layout plan. I have one on the next slide. Mark where you are going to put your scan positions so you're able to estimate how many scan positions you have. And if there is none, then definitely or always do a site inspection prior to scanning. You can use the layout plan as well as a field book. So if you're in the field, then mark where you have taken your scan positions, because perhaps somebody else is doing the registration, perhaps more than one scanner is in use and you don't know where the other person was standing around. If you don't know, if the person who is registering your project doesn't know the project at all, he was never to the project, then this layout can be a very huge help because he knows which scans are connecting to which, especially if you are not using just a normal loop, but you're putting your scanner everywhere, but not in a single loop. When using this layout plan as well, think about your feature placements, how you can have loop closures so different scans are interconnected and not only one scan to the next scan and this scan to another scan, but interconnection is very important. Think about if you're going to use geodetics. Are you using GPS points? Are you using a total station and measure yourself some checkerboard targets or something? That's another idea. If you
excuse me, geodetics, we call it in point cap geodetics. In Faroscene, for instance, it's called reference points, or in other softwares too. These points are mainly have the benefit that they are in a higher precision or in a global coordinate system have a high precision. and this will reduce some effects you will have in the registration. Okay.
And of course, you should make sure that your instruments and your scanning equipment is in tip-top shape. Use only high standard spheres and checkerboard targets. There are people out there which say, I go to the supermarket and buy some balls and just paint them white. But the issue here is that the reflectivity is then not perfectly given. Perhaps the sphere is in the intensity value image is not looking like a sphere anymore, but has some bumps and bruises, as well as checkerboard targets. I have seen a project where they just printed out checkerboard targets, and if the scanner was directly in front of them, they were completely white. You didn't see any black in there because it was just printed. Another thing is, if you use checkerboard targets, then it would be very helpful to have some numbers on it, so you only use the same checkerboard targets at the same location, so you can't mix them up by error and know which checkerboard targets in scan A is the same as checkerboard targets in scan B. But of course, just use spheres because you can see them from every direction and not only as a checkerboard target from the front. When you are on site, do a site inspection. Think about where you put your scan locations, just to make sure that you don't have any connection issues at the end and that you forgot something. And if feasible, then use on-site registration software. I know that a lot of scanner manufacturers are now getting into it, that you can use this on-site registration, and it can be very helpful if you can use it, especially if you just put one scan location after the other in a row, and they are all connected after each other. So this can be very helpful to speed up the registration in the office later on. So let's look at, for example, a layout plan. So you have here your layout plan, and then in the office already think about where you are going to place your spheres and scan locations, where you need to scan everywhere, where you need to scan, where might be issues like, for example, stairs are always a little challenge. And then you can estimate as well how many scan locations you're going to need, and of course in which resolution you're going to scan because of the scan distances here. Because in the end you want to, and in the field of course, then put in where you scanned, of course, because at the end you want to know, oh, scan 25 is connected to scan 1, but you don't know that in the office anymore when you are back after scanning. So just write it down and be safe and know where your scan locations are. This was our chapter 1. Richard, is there something to add from your side?
Not yet.
Not yet.
Any questions to the chapter 1 from the listeners?
I see none, to be honest. All right, then chapter 2, the scanning in the field. Are you using cloud to cloud or are you going feature-based? What are the differences? What are the advantages? So on the left side, you see here the cloud to cloud, or C2C, how it is called as well. And on the right side, we have feature-based. How is the matching done? By cloud to cloud, you use either point to point or point to plane or planes itself. So you have just planes which are detected in the scan. But with feature-based, you have to bring your own spheres or checkerboard targets, or you have to click your own natural features, which should be, this is just a an emergency if you are using that. Normally you just use spheres or checkerboard targets. Where are the limits? The C2C cloud to cloud has the limits. If you have no planes or normals in 3 axes, then you are not able to proceed with the cloud to cloud. Meaning, if you are in long hallways and you don't see the front or back wall of the hallway, or you are outdoors and there are no man-made objects, then the cloud to cloud will most likely fail because it can't detect enough planes in different axis directions. On the other hand, when you are feature-based and you didn't provide enough features in the scan, which is connected to another scan, then of course this will fail as well. And in addition, if you have a very bad feature constellation, for example, collinearity in your features, then you're not able to register the scans together as well. What are the time-consuming things? With cloud to cloud, you need approximation values, meaning one scan to another scan, you need the translation, X, Y, Z directions, and the rotations in omega phi kappa. So the connection between both to be able to calculate a cloud to cloud. If this is not given, for example, by GPS or by an IMU unit in the scanner, then you have to manually top view pre-alignment, pre-align your scans, or if you're lucky, they are somehow able to connect them. Often the scanning software will just, you just tell the scanning software, every scan I did is connected to the following scan, and then it will start with that, which is a sort of connection graph as well, and this might work as well. On the other hand, with feature-based, it gets time consuming when the feature extraction of your checkerboard targets or spheres is not working, because then you have to click them all manually. And if your approximation is somehow wrong, meaning scan A is connected to scan F, but in real life they are not seeing each other, and somehow this connection is done in the software. The constellation search is how the scans are connected to each other in the registration, and with cloud to cloud you connect normally one scan to another scan, and you're not able to connect multiple scans to just one scan in one search round. While in feature-based, you're able to connect the every scan to every scan because you just use this the features for the constellation. Talking about georeferencing. Do you need to georeference? Does your customer want to have a georeferenced point cloud? How can you georeference direct or indirect? And when shall you do the georeferencing? Is it necessary? As Richard already told you, it can have a big benefit that your accuracy can go up, and in addition, your scanning net is getting a lot better and more robust. On the other hand, of course, you have to measure it yourself normally because there are no points out there, so you have to bring in a total station or a GPS, and this is again, needs some time to the scanning here. Direct versus indirect. Direct means you can measure all scan locations directly. So you just measure where your scan location is and give it a global position in your coordinate. Indirect is meaning you measure the global coordinate of your feature, like a sphere or checkerboard targets, and then with the information that the sphere or checkerboard targets are at the global location, you're able to rotate the complete scans into this reference frame as well. And when shall you do the registration? You can do it in the registration or afterwards. The benefit of doing it in the registration is that you can improve the registration, but it is a little bit more computation costly, but normally this doesn't matter. On the other hand, if you do it after the registration, the disadvantage is that it is a rigid transformation, so you don't get better results by it. You just are doing a Helmut transformation on your already registered project. A word of warning here. There might be software out there which where you do the georeferencing in the registration process, but the scanning software itself will do the georeferencing afterwards and not directly in the registration itself. So it might seem like you are doing it in the registration, but the truth is you are just using the Helmut transformation afterwards and you don't see it. Richard, do you have any things to add on georeferencing or cloud to cloud?
I will come to this point at the end in the registration part a little bit.
All right. Then let's talk about the scanning itself. Now, this is the topic we have, and now we are finally here. I will talk now about scan position connections, loop closure, feature distribution, and how you should scan through a door if you are using features. And we have another point, the automatic sphere detection, when it should definitely work. Scan connections. The green suns are again our scans, and in this case you see they are connected here, meaning there are always enough features to connect these scans. But it would be a lot better if the scans are interconnected, not only a single connection, and we have a dead end here, so there's only one connection here, but it would be a lot better if they are interconnected like that. So if feasible, try to connect different scans to different scanning locations. Make sure your spheres are there so the scans can be connected using these spheres, and you get a better net there and better accuracies. Loop closures. For example, if you are scanning different floors in a building, make sure that you connect the inside and the outside. Then you are able to connect different floors by outside scans and not only going through the stairs. So in this case, you see if we now have a complete loop, the complete error distribution can be done above all scans equally and not only is laying on some scans in one row. Feature distribution. The feature distribution, as you can see here, the features are the blue balls, the scans are the green suns. The bigger the triangle of your features, the better the feature distribution, because then the angles are getting around 60 degrees and the length between the spheres are the highest. If I now connect here two different scans, it will work very good because they are seeing each other very, very nice. So this is the good. On the other hand, this is very bad because now we don't have a triangle at all. They are all in one line, in one row, and then you're not able to find the motion between two scans. You're not able to find to solve the mathematics behind it. Why is that? Because you have one degree of freedom in your calculation, meaning think of it like a bus pole. You're going to work, currently not because everybody is in quarantine, but think of it, you're going to work via bus. and you're holding to a pole. And if the bus now drives around a corner, then you feel the movement. But if you are holding two poles at the same time, you don't have this issue that you have to hold very tightly, but you can let loose a little bit. And lastly, the ugly constellation. You see the triangle is very small. It would work, but the accuracy is not very good. Of course, this is completely theoretical. I know if you're out there in the field, you can't always have the best constellation ever, but try to get the best constellation which is possible, because then you don't have a hassle with the registration. Now, lastly, to the constellations. I call it the super bad luck. Here we have our scan in the middle, and we have 60 degrees everywhere. So we have the biggest triangle possible. But why do I call it the super bad luck? Does anybody know? Because in this case, you don't know which sphere of another scan is connected here correctly. So another scan could be here, but the scan sees the sphere the same from this location or this location. So in this case, you're not able to connect these. So you have the best sphere distribution, but it's on the other hand the worst distribution as well.
Let me interact here a little bit. Go back. So for the rule of the accuracy. So to easily understand the rule is make 3 features in a constellation that the triangle area is as large as possible, and place the scan inside the triangle. This is the most stable constellation. The second I will mention is here. You can have this perfect triangle, but then the automatic constellation search will fail because you have 3 possible constellations having the same observations. What you have to do then is to manually force which feature is visible in the first scan and the second scan, and say this is the same name. Yeah, so it works, but you have to interact manually. Okay.
All right, scanning through doors. This is a configuration how you should scan through doors. You have one scan which is of course in the room, and here you have a hallway. And as you can see here, the features to connect the scan in the hallway to other scans in the hallway. And you have the spheres in the room. And in this case, you want that the scan in the doorway is able to see all scans in the room and outside of the room. In this case, the scan in the room sees 4 spheres, this, and this feature. And therefore you have a very good connection, and you're able to, or it will automatically find the constellation here and is able to go on. Another way to scan through a door would be like this, that you have 2 scans outside in the hallway, which are again looking into the room, but seeing different features on the sides. So you're able to connect here the different features again with each other with a scan in the room. Richard, do you want to?
Yes, I see. I made a mistake here. This is still possible for the registration because the scan in the room can see the feature outside. So it has 3 spheres, but the sphere on the left-hand side in the room is not visible from the scan in the room. So I made this part of the wall too large here. Yeah, you see what kind of error you can easily make if you place the spheres wrongly, because Now we have the three spheres here close to
one line. And the
one
sphere
line.
here,
This sphere is not
which would be
right.
perfect, is completely useless because it is not seen by any other scan.
Right. Yeah. So this was my fault. So then it's better to place the sphere a little bit closer to the door. Yeah. And you see the old position in the door cannot see the scan. Yeah, because of the wall. Okay.
So lastly, we have the sphere detections. When are you able to detect the spheres automatically, or when is the software able to detect the spheres automatically, on which resolution? These are again Faro scans. So you see here when we are at around 1/8, 1/5, or 1/4, we are always around 15 to 25 meters, depending of course on the sphere diameter. The higher the diameter, the more points fall onto it. If anybody is interested in the mathematics behind it, just let us know. Then we can publish how we calculated it. We calculated with around 50 points, which needs to be on the sphere to get the distances here. Just to make sure every software is able to detect them, I think in PointCap around 25 to 30 should be sufficient. So in this case, the distances, of course, will be a little bit higher up, but these are just theoretical values. I verified them with practical values from Laser Scanning Europe. They did a test here with Farosine, and the values add up. So you're able to see that the theoretical and the practical part are getting together. I have this from this website here. So last but not least comes the registration. In this case, this chapter will completely be talked through by Richard and not by me. So Richard, here you go.
Yeah, thank you. So I'd like to give a small hints regarding the registration, and we have two main registration methods. One is the feature-based registration. We mentioned already with spheres, with checkerboard targets, natural features, and planes. But planes are usually in both worlds, in the feature-based as well as in the cloud-to-cloud world. So from our clients, we know that approximately 50% are using feature-based registration and 50% are using cloud-to-cloud-based registration. My observation is that the cloud-to-cloud guys usually have smaller projects. When you have bigger projects, you usually use feature-based registration because you can more easily integrate the georeference points as reference points or geodetics to improve the registration, and the feature-based registration has also some benefits at the end. But on the biggest point or the biggest challenge in registration is the first is you need to determine the connection graph. So means which scan is overlapped with each other. And this will be represented by an adjacency matrix where you can say, okay, scan A is overlapped with scan C and D, and B is overlapped with C and F, and so on. And this is a network we showed before already. And as more dense this network is, as more stable your registration is at the end. The second thing is if you use feature-based registration, you can say, okay, which features correspond to each other in another scan? And there are algorithms out there to find this constellation automatically. But be aware, this is very complex. You need to compare each scan to each other. And this means you have a complexity of the search algorithms of n square half, or to be honest, is n times n minus 1 half.
This means to say that this means if you have 100 scans and you calculate how long the constellation search takes. It takes amount X, but if you have 101 scans, it's not only the time of processing one scan which is added, but it's double the time.
Yeah. No. Let's double. Now, when you double, if you have 100 scans, it needs 5,000 computations, and if you have 200 scans, it's already 20,000. So it's times 4 if you double the number of scans, and so on. Yeah. So the easiest thing or way to simplify this or help the search algorithms to work properly is the clustering. And we recommend to make clusters of scans between 20 and 100 scans per cluster. So this is, if you have a large building, this is easily can be easily done, but just say, okay, so level 1, level 2, level 3, outdoor scans, and so on, you put in separate clusters. And then you help the search algorithm first to have less false positives, so less errors in the constellation, and you speed up the process dramatically. So for the registration, there is sometimes a wording issue I saw on many conferences. Many people say bundle adjustment. Bundle adjustment comes from the photogrammetry. And bundle means you make the adjustment of camera positions of a bundle of rays. Yeah. To be honest, it's an adjustment. Just call the least square adjustment if you are talking about the registration mathematical method behind it. What is the least square adjustment? It's minimize the sum of the residuals. Means if you have two features in two scans and you have calculated the registration of the scans with an accuracy, and you propagate the 3D coordinate of the features in one scan and in another scan, and you create the mean, then the differences between the mean to each of the local positions in the scans for the features is the residual, and you try to minimize this. So this is what the least square adjustment is doing. So it minimizes the squared sum of the residuals. So to the feature-based model, I try to make it as simple as possible, but we have here some equations. So in the adjustment, we calculate rigid motion of each scan. So this means the X, Y, Z position and 3 angles we need. So this each scan has 6 unknowns. And we call it here H because this model we usually use is a Helmut transformation. This is the mathematical background for this projection. So we have a point X, and we multiply this with a matrix H, and we got a 3D point X in the world. So, and this X is the local position of a feature in a scan, multiplied with a matrix that contains the X, Y, Z, and omega phi kappa. And we get the world position of the feature. And if we combine this for each scan and having the correct points as its names in the list, then we have in our adjustment the unknowns 3D positions in the world coordinate, and we have the measured 3D points position and the unknowns of the rigid motion. And this is what we calculate in the adjustment. If we want to introduce the georeference observations, this means the geodetic points, then we just say, okay, we have an X coordinate of one of the feature, and this is already the world coordinate. And we need 3 of them to have so-called gauge, or the datum of your scan. Otherwise, one of the scans will be the 0 point. So this is the second observation we can have in the feature-based model. And the third one is, if the scanner has an inclinometer, we can derive from the inclinometer measurements directly the omega and kappa values and observe them directly in this model. So, and the most important part is, for each of the observations we have accuracies. So this is called the a priori accuracies. This means we can say our, let's say, spheres have an accuracy in the local scan of 1 millimeter. And our reference points come from a GPS, and the reference points have the accuracy of, let's say, 3 centimeter. Yeah, not so good, but it's fine. And the inclinometer measurement has for each angle, I think, 0.5 or 0.2 degrees. And we can introduce this in the adjustment. And this is very interesting, that after a feature-based registration, we can see how well our observations are. So we can make a full analysis and see how well our spheres are, for instance, or how well our georeference points are. This is called variance component estimation. But this is a little bit more too much in detail now. So we have a usually when we use feature-based registration, we have a global adjustment. And the global adjustment means all our raw observations are going with their accuracy into a big adjustment. And this mathematical system is very sparse. This means depends on the connection of the scans. Of course, not each scan can be overlapped with other scans, maybe each scan with 5 other scans. And therefore, we have a very sparse system, and this can be calculated also on small computers. So all the errors we have are distributed in the whole network. This is a huge benefit of the global adjustment. And for all observations, we get an posterior accuracy. This means we can check how well our estimation of the accuracy was in front. We can make a full error analysis. We can find where are maybe errors in the constellation search. We can find these errors very quickly and then process it again. And the last very good thing is we can introduce the georeference points, which reduce the drift. For instance, if you have a long corridor or a long facade and you start at the beginning and scan along the facade, then of course you have a drift. And this drift can only be compensated if you introduce this reference or georeferencing points. Good. So the second one is a two-step alignment. So this is very often used of the software in the cloud-to-cloud. So what you are doing is, with the cloud-to-cloud, you calculate the relative position from one scan to each other. So it's the same model like the Helmut transformation between two scans. Here we have point correspondences, so ICP. This is a model for ICP between the scans, and you can do calculate this independently for all scan combinations. Where you have enough overlap, you can also check is the cloud-to-cloud between two scans, does it work or does it not work? And then you have this differential registration between two scans only. So one scan is fixed and the other one is, so scan one, in this case here, scan one is fixed, and the second one will be positioned with this delta H. Good. So the next step, what you have to, and from this cloud to cloud, you can determine also the accuracy. of the 6 parameters. So, and then you put this all the relative orientations or relative motions between the scan in a net adjustment, where you say, okay, the position of your first scan multiplied with the matrix of the delta is the position of the second scan in the world. And if you put them all together, then you can make an adjustment again. And then you including also the accuracy, and then you get your whole network. The issue with that is you cannot easily introduce your reference points, because then you have a mix up between feature-based registration and yeah, two-step alignment. Yeah, you can do it, but as I know, nobody is doing this. And the second one is what many people are doing, or many manufacturers are doing. They create the clusters, calculate this net adjustment only for the cluster, and then they put the clusters together, and the clusters are rigid. And there you have a big residual stress on the cluster bounds. You maybe observe this already in some software systems. And the fourth step we mentioned already is the georeferencing, where you just make a where you pick points, 3 points or 4 points of the georeference in the scans, and then you have just a Ricoh transformation at the end. So we prefer the feature-based registration if you have big projects. Yeah. If you have small projects between 20 or 50 scans in a small area, the cloud-to-cloud is usually fine and beneficial. Yeah. If you have let's say a car accident to scan with 5 scans or 10 scans, cloud-to-cloud usually works very well. Yeah. And you have no problems. And if you can do it on field, so in a outside registration, then you are perfect. If you have big projects, we recommend to use the feature-based registration, because also you can prove your results. Yeah, in big projects, often you have big clients and they want to have a proof how accurate they are, how well the registration was, how good is the a measurement between 2 scans. For this, we invented the so-called quality metrics. Nowadays, also Faro and Leica have this in their registration sheets to take over this, and there you have behind how well your registration is visualized in a matrix, in a colored matrix. What we always recommend is, for big project, introduce high accuracy control points, so the geodetics with GPS and total station. It helps you, you have the georeferences immediately, and it helps you to compensate the drift. The drift is for big projects usually a big problem. Yeah, you can roughly say if you have a big hall and you scan the big hall, it's maybe 100 meter in diameter, you have 5 centimeters in drift when you not use high accuracy control points. Okay, so this is a little bit to the registration. Of course, the in the registration, the graphical user interface and the interaction to find the errors you made or the automatic registration made, we think this is the most important point in the software. In PointCap, we try to optimize this for the feature-based registration. It cannot be perfect, but if you understand how registration works, then these features we have in PointCap will help you to find easily the problems. Of course, with Scantra, for instance, they use features or plane features, and they introduced now also the automatic, fully automatic registration in clusters between 50 to 100 scans, I think so. It works. I did not see it directly, but they mentioned that it works very well already. And it's between the cloud to cloud and feature-based registration. So they use cloud to cloud for the constellation search and feature-based registration afterwards in a big adjustment. Good. So I think we are at the end. Martin, do you have some recommendations here?
To the registration itself, not,
Yeah.
but there were some questions.
Oh, I did not see it. Okay.
So the first question was that we go back. Perhaps I guess it's all right if we hand out the PDF or put it online so you can have a look afterwards, because scrolling through the video might be a hassle. So we put it online, and we'll send the link in the after email we will send out. The question was, can you explain again how to connect a scan to a following scan and so on? How do you do it exactly, step by step? And regarding on a room. So as we already mentioned before, is you need at least 3 features in 2 different scans which are identical. So this sphere in the left room corner at the top is seen from this scan, and it is seen from this scan as well. We call this scan A and scan B. And you need at least 3 features in both scans to be able to find a connection between those 2 scans. So if you only see 2 features which are identical, then you're not able to connect them. And in this case, you have to use, you have to set your own point, which is of course a lot less accurate as if you have a feature here, because on a sphere a la 50 to, a lot of points, which will estimate the middle point, while when you just click one feature and say you click on the wall at a certain location, it is not as accurate. Of course, this is going into the alignment, your set point with a certain accuracy, but still you should see at least 3 features. 4, as we have it here, is a lot better, because then you can in addition calculate the error propagation to different scans.
So the second question. So this was the first question. Okay. The second question is, on the second day, if you have projects for multiple days, of course, you have your spheres you want to take back to your hotel, and usually use stickers to put on the positions and to place the spheres on the next day. So the question is, so if we don't place on the sticker, usually 3 for connection, it gives an error and we need to add points.
One way would be to for the end of the day and starting next day scans, you could, for example, use self-printed checkerboard targets and then just let them hang overnight. This would be one way, but I don't see another way as to use stickers and then set the spheres up again, because in this case you are on the safe side, because somebody else could, for example, get rid of the checkerboard targets. You never know. So I don't really see an idea how you can go around to place the stickers and play and put the spheres back up on the next day onto these stickers. In addition, I mean, if you're scanning outside and then you're going inside and you're doing a connection scan from the inside and the outside, then of course you need to put the spheres outside up again as well. So you need a sticker there as well.
Yeah, what you can do, in addition, you can use the color spray. Yeah, it's color spray with a mask. Then nobody can remove the stickers. This is the last option if it's allowed to do this. Yeah. Okay. Okay, the next thing is the question was, can we do this again in German language? Martin.
Should be possible. I
Okay,
mean, we have an open slot for next week, so we can do the same in German next week as well.
okay, yeah, I think so. So we will give you all the necessary information for new webinars in the next on Monday, I think. Yeah, for the next week. And as long as this pandemic is running, as more possibilities for this webinar will be there. Okay. Question 2.
It was, I think it was about how to connect scans. What should you expect as max distance between scans? This is depending on the resolution with which you are scanning. I mean, if you have a lot of time and you have a big area, of course you're able to go full resolution and then set your scan up every 100 or 200 meters. Of course, think of the distance error in this case. On the other hand, you can go to a lower resolution and do some more scans. But I think there is no issue going to longer distances as long as the resolution matches what you need in point density, and of course if you're able to see enough features.
So I think
Richard,
you
okay,
not a
last question, and then we will finish it. For Richard, should you place the spheres at various heights?
No, it's not necessary. Yeah, we observed this. Some people said, okay, you have two reference spheres on the ground, and then you have one as high as possible. No, it will not influence the accuracy. The accuracy just depends on the triangle size and is the scan inside this triangle, yeah, mostly. So the high of the points doesn't matter. But if you have a big factory, it's sometimes very good to have the spheres as high as possible because you can see the spheres from multiple positions. Yeah, in this case, it's good. But if you have free line of sight, it's not necessary. So it will not influence the accuracy. I hope this makes sense.
All right, Nicole, do you want to wrap up?
well,
wait. Here's the last question. What should you expect as max distance between scans? This is a question we hopefully discussed with the resolution of the scans and how well you can detect the spheres from the distance. So there is no maximum distance we can say. It depends on your project and of course of how large are your space and how much time do you have for scanning and what point density you want to have on your object. Yeah, this depends highly on your project. We have clients. They said we make less scans No, we make smaller resolutions, so 1/5 or 1/8, but more scan positions. Yeah, and then we have more overlap. The registration is in the same speed, but also other people say no, I make higher resolution and go farther away. You need to check it out by yourself. I cannot really say it because I'm not in the practice involved so much. Yeah. Okay, good.
Okay,
Nicole.
so yeah. I see some like 1 or 2 more questions from Stephen and Eamon, but I guess if you want to wrap it up right now, we can try to answer them via email. Thank you all for being here, and don't forget to sign up for next week.
Have a nice weekend. Bye bye.
Thank you very much. Bye bye.